Chapter 13, Divergent Boundaries. An emerging picture of the ocean floor. Mapping the seafloor from 1872 to 1876, the HMS Challenger collected oceanographic data, measured the depth to the seafloor by lowering weighted lines overboard. The deepest spot measured is now called the Challenger Deep. Mapping the seafloor. Modern bathymetric techniques. The topography or shape of the ocean floor is called bathymetry. Sonar, using sound energy, is now used to measure the depth to the ocean floor. Early bathymetric profiles were created using echo sounders, which bounce the sound off an object to determine the distance. So here's our echo sounder. So off the ship, they send out a signal, and they count the amount of time for it to hit the seafloor and return, and divide by 2, and use the speed of sound in order to determine the distance. Okay. Modern bathymetric techniques use side-scan sonar images as horizontal region above the seafloor. High-resolution multi-beam instruments send out a fan of sound and record reflections from various receivers to provide a more detailed view of the ocean floor. Only about 5% of the seafloor has been mapped in detail. So here's a diagram of side-scan and multi-beam sonar. So here we have our side-scan, the little towfish, and here's a multi-beam sonar. Okay, here's what it starts looking like, maps things nice in 3D. Now here's a contour map showing bathymetric lines of equal depth. Mapping the ocean floor from space. Massive underwater structures exert stronger than normal gravitational attraction. Water piles up over these features. So the surface of the ocean kind of generalizes what's below it. So satellite radar altimeters can detect changes in elevation of the ocean's surface. So I used a satellite, and I was using a radar altimeter to bounce radar waves down and reflect them back up. And you end up with somewhat of an ocean surface. Now, it doesn't mean it's perfect. Like right here is a peak where there's actually more of a basin. So this is an anomaly in the data collection. Provinces of the ocean floor. The 3 major areas of the ocean floor based on topography. There's the continental margins, which are the outer margins of the continents that transition to ocean crust, the deep ocean basins between the continental margins and the oceanic ridge, and the oceanic ridges, a broad linear swell at the divergent plate boundary. Okay, so let's say we look at a profile from North America to Africa. Okay, in the middle, here's the mid-ocean ridge. Okay, so here we see that mid-ocean ridge in the center. Here's the continental margin at point A on North America. Here's the continental margin at point B over in Africa. Here's a deep ocean basin between. Okay, so here is the continental shelf. Here's our continental slope at 2. There's our continental rise for 3. Here's a little seamount, a little volcanic seamount. Our abyssal plain is a flat area. Okay, so here's our rift valley. Okay, there's abyssal plain again, a seamount, continental rise, continental slope, and our continental shelf. Passive continental margins found along most coastal areas that surround the Atlantic Ocean, not associated with plate boundaries, experience very little volcanism and few earthquakes. A continental shelf is a gently sloping, flooded portion of the continent. It varies greatly in width. It's gently sloping, contains important mineral and oil deposits, and some areas contain extensive glacial deposits, and it's important fishing grounds. The continental slope is a steep structure that marks the boundary between the continent and the ocean. Okay, continental and ocean crust. The inclination varies, but the average is about 5 degrees. The slope in some areas is as high as 25 degrees. The continental rise is a thick accumulation of sediment from the continental slope. These sediments are typically carried by turbidity currents, which is mixtures of sediment and water that flow down submarine canyons. When a turbidity current emerges onto the relatively flat ocean floor, the sediments spread out in a fan shape called a deep sea fan. The continental rise is composed of multiple deep sea fans. Okay, so here's our continental shelf, the continental slope, and here's our rise, which is built up from deep sea fans of sediment deposited with turbidity currents going down these submarine canyons and depositing material in these deep sea fans. Active continental margins, where oceanic lithosphere is subducted beneath the continent, often associated with deep ocean trenches located primarily around the Pacific Ocean. Sediments and rocks can be scraped from the ascending plate and accumulate on the continental plate, called accretionary wedge. Subduction erosion occurs when subducting plate scrapes the bottom of an overriding plate. It's effective when the angle of the descent is steep. Okay, so here with oceanic crust converging with continental crust, the oceanic crust is subducting. As it's subducting, parts of it are scraping off on the continental crust, forming this accretionary wedge. Also, this could also be eroding the underside of the continental crust. So, deep ocean basin. The features include deep ocean trenches, abyssal plains, seamounts and guyutes, and oceanic plateaus. The deep ocean trench is a long, narrow crease that represents the deepest part of the seafloor. Challenger Deep in the Mariana Trench is the deepest spot in the ocean, 10,994 meters below sea level. Surface expression of a subduction zone associated with volcanic activity, volcanic island arcs and continental volcanic arcs, mostly found in the Pacific Ocean. Challenger Deep, Challenger Deep is located here. This part of the picture is like right here. Okay, here's the Marianas Trench. Abyssal plains, flat features of the ocean floor, likely the most level places on the Earth. Sites of thick accumulations of sediment, fine sediments from turbidity currents, minerals precipitated from seawater, shells and marine plankton, found in all oceans, most extensive in the Atlantic Ocean. Seismic reflection profile of the ocean floor. So here we have, so we're an explosion, so we have some sound to bounce off the ocean floor, so we can try to see what's underneath these sediments. So here is bedrock of the ocean crust underneath these layers of accumulated sediments. Volcanic structures on the ocean floor, seamounts of volcanic islands. Submarine volcanoes are called seamounts. Over 1 million seamounts exist, found in all ocean floors, most common in the Pacific. Many form near ocean ridges over a hotspot. A seamount may grow large enough to emerge as a volcanic island. Examples are the Easter Island, Tahiti, Bora Bora, and the Galapagos Island. Guyutes are submerged flat-top seamounts. After a volcano is extinct, it eventually erodes to sea level, where waves flatten the top of the structure. As the plates carry the structure away, it eventually lowers into the ocean. Oceanic plateaus, vast outpourings of basaltic lavas on the ocean floor. An oceanic ridge or mid-ocean ridge or rise is a broad linear swell along a divergent plate boundary, the longest topographic feature of the Earth. It occupies elevated positions. Segments are offset by transform faults, extensive faulting earthquakes, and a rift valley. A deep down-faulted structure exists on the axis of most ridges. And this winds around from one ocean into another, so it winds through all the major oceans. That's why it's the longest feature on the Earth. Seafloor spreading. This concept was formulated in the early 60s by Harry Hess. Seafloor spreading occurs along the crest of ocean ridges. Newly formed melt from decompression melting the mantle slowly rises towards the surface. Most melt solidifies in the lower crust, but some escapes to the seafloor and erupts as lava. Why are ocean ridges elevated? Newly created lithosphere is hot and less dense than surrounding rocks. As newly formed crust moves away from the spreading center, it cools and increases in density. Spreading rates and ridge topography. Ocean ridges with slow spreading rates have well-developed rift valleys and rugged topography. Ocean ridges with intermediate spreading rates have subdued rift valleys and topography. And oceanic ridges with fast spreading rates generally do not have a rift valley, but a shallow profile. Okay, so here, topography, you have slow and fast spreading centers. So here, a slow spreading center gives plenty of time for that partial melt to develop and flood, flood out and to build up a nice rugged terrain. Here is a fast spreading center. Okay, so valleys do not develop and the topography is comparatively smooth. Oceanic crust has 4 distinct layers. The sequence of 4 layers composing the oceanic crust is called an Ophiolite complex. Layer 1 consists of deep sea sediments and sedimentary rocks. Layer 2 consists of pillow basalts. Layer 3 consists of numerous interconnected dikes called sheet dikes. And layer 4 consists of gabbro, okay, which is a coarse-grained basalt. Okay, so here, layer 1 are deep sea sediments. Layer 2, we have basaltic pillow lavas. Layer 3 is a sheeted dike complex. Layer 4 is a gabbro. Okay, and then we may have down here is the mantle, peridotite. How does oceanic crust form? Basaltic magma originates from partially melted mantle peridotite. The mantle rises through the upper mantle in tiny cracks until it reaches a lens-shaped magma chamber beneath the ridge crest. As the pressure in the chamber increases, the rock around the chamber periodically fractures. Magma ascends through these fractures, cools, and solidifies to form a sheeted dike complex. 10 to 20% of the magma reaches the seafloor where it quickly solidifies, forming large tube-shaped protuberances known as pillow basalts. So here's the erupted pillow lava forming this pillow-shaped, it solidifies in these pillow shapes. Interactions between seawater and oceanic crust. Permeable and highly fractured crust allows seawater to penetrate the crust by 2 to 3 kilometers. Seawater is heated as it circulates through the crust, altering the basalt by hydrothermal metamorphism. Hot groundwater dissolves ions of various metals from the rock and precipitates them on the seafloor as particle-filled clouds called black smokers. Continental rifting, birth of a new ocean basin. A new ocean basin begins with the formation of a continental rift. So it's an elongated depression where the lithosphere is stretched and thinned and the continent's about to break apart. When the lithosphere is thick and cold, rifts are narrow. Examples include the East African Rift, the Rio Grande Rift, the Baikal Rift, and the Rhine Valley. When the lithosphere is thin and hot, the rift can be very wide. These examples include the Basin Range in the western United States. East African Rift. Continental rift extends through eastern Africa, consists of several interconnected rift valleys. Normal faulting leads to grabens, or downfolded blocks. The area has expansive basaltic flows of volcanic cones. And here's our East African Rift Zone here. There's several different rift branches. And here's where it's a little wider. Okay, this evolution of ocean basins still. The Red Sea, formed when the Arabian Peninsula rifted from Africa, began about 30 million years ago. Fault scarps surrounding the Red Sea are similar to structures seen in the East African Rift. As spreading continues, the Red Sea will grow wider and develop into an elongated mid-ocean ridge. The Atlantic Ocean. After tens of millions of years, the Red Sea will develop into a feature similar to the Atlantic Ocean. As new oceanic crusts are added to diverging plates, the rifted margins move farther from the region of upwelling. These margins cool and subside below the sea level. Okay, so here is here's an example of when South America broke away from Africa. There was a rift valley zone here. As the plates spread apart, that rift valley turned into more of a whole basin and became an ocean basin. Interrupted rifting. A frail rift valley extends from Lake Superior into Kansas. Formerly active rift valleys filled with basalt and clastic sedimentary rocks. Why rifts fail or succeed is not fully understood. So here, here's this failed rift valley. Extends all the way out to Kansas. The gray is volcanic rocks, and the orange is clastic sedimentary rocks. Mechanisms for continental rifting. The supercontinent cycle is the formation and dispersal of supercontinents. 2 supercontinents have existed in the geologic past. Pangaea was the most recent, and Rodinia was the prior one. It involves major changes in the direction and nature of the forces that drive plate motion. Mantle plumes and hot spots. Regions hotter than normal mantle rise, experience decompression melting, and create basalts that trigger hotspot volcanism on the surface. Mantle plumes concentrate under thick continental crust, which traps heat in the mantle. Hot mantle plumes eventually cause overlying crust to dome and weaken. And flood basalts can precede rifting events. Okay, so here's possible mantle plumes in the breakup of Pangaea. So here's Pangaea. These red dots are where there were possible major mantle plumes, which weakened the crust and caused rifting. They allowed Pangaea to break up. The doming of the crust can produce 3 rifts that join in an area above the rising mantle plume called a triple junction. Continental rift usually occurs along 2 arms. The 3rd arm becomes a failed rift. Mantle plumes do not always lead to rifting. Example, the Columbia River basalts in the Pacific Northwest has not led to rifting. The role of tensional stress. When crust is thin and hot, small stresses are sufficient to initiate spreading. For example, the Basin and Range region of the western United States. Slab pull from subducting plates can create sufficient tensional stresses to initiate rifting in the Pacific Northwest. Why oceanic lithosphere subducts? This is how just the oceanic lithosphere gets destroyed. The fate of oceanic crust is still being debated. It pile up at the boundary between the upper and lower mantle. It subducts to the core mantle boundary. Okay, those are two possible outcomes. Overall density must be greater than the underlying asthenosphere. Spontaneous subduction. Very old, thick, dense lithosphere sinks into the mantle by its own weight, results in descending angles nearly 90 degrees. For example, the Marianas Trench. Lithospheric mantle is what drives subduction. Okay, so here we have very old, cold, dense lithosphere subducts at a steep angle. So there's like the Marianas Trench. Young, warm, buoyant lithosphere subducts at a lower angle. Force subduction. Younger, less dense lithosphere is forced beneath overlying plate by compressional forces, descends at shallow angles. For example, the Peru-Chile Trench. Subduction plates, the demise of ocean basins. If a plate subducts faster than it's produced at the spreading center, the plate will get smaller until it completely subducts. For example, the Farallon plate. So here's the Farallon plate in between Pacific plate and North America, and it's slowly being destroyed. It's like almost gone today. It's the end of this chapter.